Here in this example, we want to look at the mean value theorem, and it's going to deal with the vertical motion of an object. We have the height of an object t seconds after it is dropped from a height of 500 meters is given by the following function, and this is the position function. S of t equals negative 4.9 t squared plus 500. Find the average velocity, and the key word here is we're looking for the average velocity of the object during the first 3 seconds. Okay, so that's our first step. Then secondly, we want to use the mean value theorem to verify that at some time during the first 3 seconds of the fall, the instantaneous velocity equals the average velocity. All right, so if we look at the first, we want to calculate the average velocity during the first 3 seconds. Now, this is our position function. And if we graph our position function as I've done here, I'm using the viewing window of -3 to 15 on the x and -5 to 525 on the y-axis. So you'll notice here we have the path of our object. So here we are 500 at 500 here, and we want to find the average velocity of the object during the first 3 seconds. So here we start at our height of 500, and then if we count over 3 seconds, then we want to know what is the average velocity from here to here. So if I was to actually go through here and draw our line, we want to know what is this average velocity. Well, the velocity average, if we think of the mean value theorem, then we're going to take f of b minus f of a over b minus a. So once again, all we're doing here is looking at the slope, or the rate of change, from 0 to 3 seconds. So that means we need to evaluate the function at f of b, which would be 3. So f of 3 minus f of 0 over 3 minus 0. So once again, that means we're going to plug 3 into our position function. So if we do that here, what are we going to get if we plug 3 into our position function? Well, we're going to end up with 3 squared times a negative 4.9 plus 500. So that's going to equal 455.9 minus f of 0. Well, if we plug 0 in, we're going to be left with the 500 and 3 on the bottom. So we're going to have 455.9 minus 500 divided by 3 is a negative 14.7, and this is going to be meters per second. And this is our average velocity. So on average, from 0 to 3 seconds, our velocity is a negative 14.7 meters per second. All right, now number 2 says we want to use the mean value theorem to verify that there is a time during the first 3 seconds that the instantaneous velocity is going to be equal to the average velocity, and they want us to find that particular time. So somewhere from 0 to 3, and this is going back to that, we want to find kind of that C value in here. What value, if we pick a point within this interval from 0 to 3, what point on the graph is going to give us a line that's parallel to this secant line? Well, in order to do that, we're simply going to take the derivative, because if we're looking for the instantaneous rate of change, we know that we're going to take the derivative of this function. So if we're looking for s prime of t, what is that going to be? Well, negative 4.9, so you're going to multiply that by 2, and we end up with a negative 9.8 t. Now, do you recall once we take the derivative of our position function, what does that equal? Well, remember, this here then is your velocity. Okay, so this is our velocity now. Remember, if we talked about that before. And just kind of as a side note, if we take the derivative here of the velocity, what do we get? We would have the acceleration. And if we take the derivative here, we would have negative 9.8. And that is the, for those of you that have had physics, negative 9.8, that is the acceleration due to gravity. So if we take the derivative, we have a constant acceleration of negative 9.8 meters per second squared, which simply means that the gravity is pulling this object down. That's why it's negative at 9.8 meters per second squared. Now, for our problem, we're concerned with the velocity. Well, we have a negative 9.8 t, and we want to know at what time is our velocity going to be equal to the average. So we're going to take our negative 9.8 t and set it equal to a negative 14.7. And if we solve for t, negative 14.7 divided by 9.8, we end up with 1.5 seconds. So at 1.5, so right here at 1.5 seconds, the instantaneous velocity is a negative 14.7 meters per second. Now, to kind of emphasize this a little bit more, for example, if I wanted to look at s prime of 1, at 1 second, what is our instantaneous rate of change? Well, if we plug 1 in for t, we have a negative 9.8. So that means at 1 second, we're going at negative 9.8 meters per second. And then what happens at s prime of 1.5? Well, we know at 1.5 it's a negative 14.7 meters per second. And what happens at 3 seconds? Well, at 3 seconds we would have a negative 29.4 meters per second. So if you notice, the instantaneous rate of change at 1 second here is a negative 9.8 meters per second. And then at 1.5, it's a negative 14.7 meters per second. And then at 3 seconds, it's a negative 29.4 meters per second. So here in the green, we're looking at the instantaneous rate of change at those specific time. Whereas in the purple here, we looked at from 0 to 3, the average rate of change from 0 to 3 seconds. So if you notice here, we found the average velocity for the first 3 seconds, and all we simply used was, for the average, our slope formula, y2 minus y1 over x2 minus x1, and we had a negative 14.7 meters per second. And to find the instantaneous velocity, we simply took the derivative, and then if we set that equal to the negative 14.7, we found that at 1.5 seconds, the instantaneous velocity is going to be equal to the average velocity.